In this video, I discussed the product between two vectors called the dot product and its two main applications for us, which is finding the angle between two vectors and finding the projection of one vector upon another. Now, the dot product between two vectors from the exact same space, so from Rn, so they have the exact same number of components, is defined to be that u dotted with v is you take the product of the corresponding components for the vectors and then just take the sum of those products. So for example, if I wanted to find the dot product of these two vectors, the dot product of u with v would then be, take the first components, that'd be 1 times -1, take the second components, that'd be 3 times 4, and then just add those products. So that dot product would be 11. Now that we have the definition of a dot product, we need the algebraic properties of it. So what we want is that the product, the dot product, between two vectors mimics in a lot of way just normal multiplication between numbers. So for that reason, if you have two vectors of the exact same size and some scalar c, then the dot product u dotted with v is going to have to equal v dotted with u. We want this property because that way we can do commutativity. And again, get ready for using common techniques we use to collect like terms. Now we need some way to describe how the dot product relates with scalars. So the second property says that if you have a dot product and the first vector is a scalar multiple, you can just take that scalar out. So you're able to move scalars in and out of a dot product. You can do the dot product before dot products, or you can do the dot product before scalar multiplication, or you can do the scalar multiplication and then the dot product. The third property is how the dot product interacts with vector addition, and it just distributes through. That's great. The last one sounds a little strange. The dot product of a vector with itself has to be non-zero. Or if it is zero, then it must be the zero vector. This is nice to note, but it's not hard to see, because if you take a dot product of a vector with itself, you are taking a sum of products, but each of those products is the product of an entry with itself. You're essentially squaring the entry. So the dot product of a vector with itself is the sum of the squares of its entries, of its different components. And that's got to be non-zero. And the only way it can equal zero is, well, if all the entries are zero. So the vector would then be the zero vector. Now, these properties, though, are things that we're going to use in general as we move on to more abstract vectors towards the end of the course. So you need to see why certain properties are true. I'm going to give you a real quick proof. So let's go and prove that the scalar multiple of a vector dotted with another is the same as just taking the scalar multiple of the dot product of those two vectors. We'll do it by component. So we'll start by looking at the left-hand side and we'll algebraically transform it to the right. So let's just declare two vectors u and v in the normal way. So then the vector u will have components u sub 1, u sub 2, up to u sub n. And v is the same. It'll be a vector whose components are v sub 1, v sub 2, and so on. And just let c be some scalar. Now, if you look at the left-hand side of the thing I want to prove, c times u dotted with a v. We know what c times u is. You just multiply the scalar through the vector. So then I have the dot product of just these two vectors. We then just take the product of corresponding components and then take the sum of those products. That then gives me that. That's just literally the definition of what the dot product means. Notice though that every single product has a common factor of c. Just pull that c out. That's the normal distribution property of reals. Then you notice that you have a sum of products, u1 times v1 up to un times vn, and you're taking the sum of those products. That's a dot product. That in fact is just c times the dot product of u with v. And that's it. That's the proof. It's really very simple. This is called a proof by component. You're just literally looking at the left-hand side and bringing down the components, doing the operations, and then unraveling it to get the right-hand side of the equation. The proof is usually very straightforward. Now, these properties allow you to be really kind of cavalier with how you use scalars. Don't feel compelled to do dot products with the way things stand. you can go and use the properties of scalars and dot products to handle all scalars, and therefore any kind of common factor between the components afterwards. For example, what if I wanted to find out what this particular product is? Now, I could multiply the two through to get the vector 10, 20, and then do the dot product. Sure, I definitely could do that. I choose not to, though. Instead, I'm going to notice that, do you see how 3 is a common factor of the second vector? Do you see how 5 is a common factor of the first vector? I'm going to pull those scalars out. That's just one of the properties of scalar multiplication. But then, because of scalars and how they work with vectors, you can reassociate these. So the 2 times 5 is just 10, and the 3 is 30. Because of the properties I just showed you, you're allowed to take actually all those scalars and just take their product and put them out front. The benefit of doing this is now you're taking a dot product with simply much simpler vectors, 1, 2, and -1, 2. That dot product is 3. So the dot product of the original two vectors is just 30 times 3, that's 90. Now your very first instinct will probably be, that looks more difficult. Why don't I just multiply it out? It's because I'm trying to teach you what to do when you don't have numbers. If you have symbols only, how do you deal with things? Because that's what we're aiming towards. You're not going to have vectors where you see numbers, not after about 2/3 of the way through the course. But these algebraic properties will still stick behind. Okay, just to show you what I mean, let's try one last one. I want to practice some algebra with dot products. I'm going to do it the long way. I'm literally going to write down everything. It's going to be quite a lot of work. But you'll see in the end that the dot product is a lot like just normal multiplication between vectors. You literally just distribute things through. You would call it foiling. So I'll show you. I'm going to prove that if you take the sum of u plus v and dot it with itself, u plus v, it's equal to u dotted with u plus 2 times u dotted with v plus v dotted with v. Again, the proof is very easy. This is not a proof by component. It's just using the algebraic properties. So if you have u plus v and you take this dot product with u plus v, one of the properties of dot products is that you can distribute through a sum. So for this vector, I will distribute it through the sum. That will then give you u plus v dotted with u plus v, and that is dotted with u. Now, because dot products are commutative, you can change the order. You can change the order of the, uv, sorry, I copied there, uv, here we go. You can change the order of the dot product. So if you want, you can think of this as u dotted with the sum. So you can distribute this dot product also through the sum, even though the sum is in the first portion of the dot product. That would be u dotted with u plus v dotted with u. I'll do the same thing for the second one. That'd be then u dotted with v plus v dotted with v. And then lastly, again by commutativity, this term and that term are actually the same thing, because u dotted with v is the same as v dotted with u. That then gives you u dotted with u plus 2 of these terms, u dotted with v plus v dotted with v. And that is what I had to prove. It's very, very simple. It's not very difficult at all. Now that we have the dot product and its algebraic properties, we can use it to define what we mean by the length of a vector in general, but do it algebraically as well as doing it on components. So if you give me a vector u defined normally as components u1, u2 up to un, then the length or magnitude of that vector, which is u with a double bar, notice it's 2 absolute values kind of like around the u, it's defined to be the square root of the dot product of the vector u with itself. So it's just the square root of the sum of the squares of its components. It's literally the normal definition of the distance of a point to the origin. Notice though, algebraically, this also means that the length of a vector squared is just the same as saying the dot product of a vector with itself. That's a nice connection, because that way we don't have to introduce entirely new properties. We can just go and use the old properties of the dot product to derive new properties for the magnitude of a vector. So I think that you probably should see a quick example. So if I said, what's the length of the row vector 1, -2? By definition, it's literally just take the square root of the sum of the squares of the components. So that magnitude, the length, is just the square root of 5. Now, next, let's go look at a theorem giving you the algebraic properties of the norm. Now, these are the main ones. There's, of course, others in this. Suppose you have a vector u in Rn, and let C be any old scalar. Then the length of a vector is 0 if and only if the vector is 0. That means then if the length is 0, the vector is 0. And if the vector is 0, its length is 0. That's pretty obvious, I hope. The second one, though, is a huge computation time saver, that if you ever take the length of a scalar multiple of a vector, you can take the scalar multiple out of the length operation, just take its absolute value, and take the length of the vector. And then just take the product of that absolute value of the scalar with the length of the vector u. It's great. It means that you can move scalars kind of in and out of lengths and not worry about it so much, as long as you take the absolute value of the scalar. Can't forget that part, because the length in the end must be non-negative. So that last one's pretty important, so I think it's important to show you how to prove it. I'll do it just using the properties we already have. So I'm going to prove that the length of a scalar multiple of u is the absolute value of the scalar multiple times the length of u. And then I'll show you how to use it. Notice, by definition, that the length of the vector cu squared is just the dot product of that vector with itself. But with scalars, we can move scalars like all over the place because of the properties of the dot product. So we just gather all those scalars, c, twice, and just put them out front of the dot product, u with u. So c times c is c squared. That means then that the length of cu squared has to equal c squared times the length of u squared. And that's because u dot with u is just the length of u squared. Now, notice on the left side of that equation and the right hand side of the equation you have squares. So just take the square root of everything on both sides. When you do that, you have to recall that when you take the square root of c squared, it actually doesn't cancel. It's the absolute value of c. So if you just take the square root of both sides of that equation, left and right, you get the statement that the length of c times u is just the absolute value of c times the length of u. Again, a really simple algebraic proof. This one not done by components, but by using the properties that we know. I want to show you then how to go about using that. So what if I wanted to know the magnitude of this vector? So there's a number of ways to handle it. But I hate working with fractions. So if I were to do the problem, I'd be a little sneaky. I'd say, hey, to find the length of the vector 3/4, 1/6, I'd notice, do you see how you can take a common factor of 1/12 out of that? To get, if you take 1/12 out of 3/4, that would then give you a 9. And take 1/12 out of 1/6, and that would give you then 2. So the length then is, you can take the scalar out, just take its absolute value, and take the length of the vector that's left behind. That would then be 1/12. This would then be the square root of 9 squared plus 2 squared. That is the square root of 9 squared is 81, 2 squared is 4. That's the square root of 85 all over 12. And that's the answer. Isn't that nice? That means you don't have to deal with strange fractions with a lot of these problems. You can just take those scalars out, because scalar multiplication, both for the dot product and for the magnitude of a vector, we have some really nice properties. So please take advantage of this. Please don't just take 3/4 and square it, take 1/6 and square it, and then add those squares. You're now adding fractions. That's no fun. Now you need to have common denominators. This is just a lot faster. although it's not intuitive. Now that we have the properties of the dot product and length, we can then move up to special kind of vectors. You've already seen some of these. These are called unit vectors. A unit vector is just a vector whose length is 1. And any vector whose length is 1 is called a unit vector. In R2, that'd be the unit vectors in the plane. All unit vectors in the plane have a one-to-one correspondence with all the points on the unit circle. Now, you have already been exposed to certain types of unit vectors. Those were called the standard unit vectors. We call them E1, E2, E3. So then E2, for example, in R4 would be a vector with 4 components whose second component is 1 and the others are all 0. That'd be a vector of length 1 just by using the normal definition. The reason we do this is because the unit vector, since the unit vector's length is 1, its magnitude is 1, it's a vector that essentially doesn't have length because it's just 1. It's the same as every other unit vector. So unit vectors are a convenient way to describe direction only. So I want a vector v that's in the same direction as v, but it's just length 1. To do that, you take the vector v and you just divide by its length. That would then be a vector in the same direction and whose length is 1. Why is it in the same direction is easy, because if you take the vector and you ever multiply a vector by a non-negative scalar, you don't change its direction. You might change its length, but you don't change its direction. So at least in the same direction as v, because you're dividing by a positive number. Notice you can only do this though if the vector is non-zero, because if it's a 0 vector, you then be dividing by the length of 0, which is 0. So you can't do this with a 0 vector. The process of finding this unit vector is called normalizing the vector. So we can ask the question 2 ways. Give me a unit vector in the direction of v. Or you could just say normalize the vector v. They're the same thing. Now, why is this true? I have to check why is it that the length of the new vector is 1. It just boils down to the algebra you see here. Take the length of the vector, divide by its length. But 1 over the length is just a scalar. You can take that scalar in and out of the length operation. So just take it out and take its absolute value. But the absolute value of 1 over the length of v is already positive, so you don't need the absolute value. That means then you have the length of v divided by the length of v, and since v is not a 0 vector, those are non-zero numbers and they cancel, giving you 1. That's why it works. Again, a quick, easy algebraic proof based upon the properties that we have. I'm trying to get you to learn the algebra to get you ready for long term, where you're not going to see numbers. You're not going to see the components. We're going to work on a much higher level than that. So let's just do a quick example. Let's find a unit vector in the direction of the vector -1, 3. So that vector would then just be, take the vector -1, 3 and just divide by its length, which is the square root of -1 squared plus 3 squared. Notice you can write that vector. I'll call that vector u. That vector can be written as 1 over the square root of 10 times the vector -1, 3. Notice I chose not to multiply the scalar through because, as you've seen in the rest of this video so far, we can kind of play around. We can be very cavalier with how we use scalars. So just leave the scalar up front. There's plenty of times when we don't want to multiply it through. Sure, every now and then, once in a blue moon, we actually want to multiply it through and get a vector with just components, not a scalar multiple of a vector. But sometimes it's a good idea to think of a vector as a scalar multiple of another. This is actually one of those choices. Let's normalize the vector 5, 10. When I see the vector 5, 10, I see the vector v, which would then be the vector 5, 10. But you can think of that as 5 times the vector 1, 2. Bear with me. Bear with me. So I want to know what would be the vector u that's in the same direction as v, but whose length is 1. I could then think of that as take v and divide by the length of v. Now don't actually do the computations. Let's think of it in terms of what you've already learned. So this would then be v, which is 5 times 1, 2, and that'd be divided by the length of that vector. But the length of a scalar multiple times a vector is the absolute value of that scalar times the length of that vector. Notice how the absolute value of 5 is just 5, so the 5's cancel. We never even need it. So instead we then have the vector 1, 2 divided by the square root of 1 squared plus 2 squared, and that is 1 over the square root of 5 times the vector 1, 2. And that's it. That's how you would do that. That's how I would do that problem. Notice then if you ever want to find the length of a vector and you see some scalar you can take out, do it, because it doesn't matter. That scalar will vanish in the computation. So the next thing would then be is if you're given two objects in the plane, you can find the distance between them by just using the normal everyday distance formula. Well, we want to be able to do the same sort of thing with vectors. We want to find their distance, which is weird because you can put vectors anywhere, right? You can, in a plane, two vectors are equal just if their components are the same. And if you have them start at the exact same origin, what's their distance? Because they're touching, right? But we need some kind of algebraic way that gives a meaningful reason or definition of distance between vectors. We're going to use basically the normal everyday distance formula between 2 points. We'll just use the two vectors, we'll put them in standard position, we'll look at the terminal points of those vectors, and we'll just find the distance between those 2 points. It winds up being then that if you give me two vectors a and b, the distance, which is given d of a comma b, is literally then just the length of the vector a minus b. Remember, the vector a minus b goes from terminal point of a to terminal point of b. So the length of that is literally what I just said as the distance between two vectors. It's just the distance between the terminal points of the vectors when they're in standard position. So I gave a general formula if you want the components. This is a formula that we never really use. It's nice to know, but we really never really use it. We bring everything down just to lengths anyway and don't worry about the idea of distance between vectors. But what we do need is the idea of an angle between vectors. That one we can visualize because the vectors in their standard position. There's a rotation between those vectors. We want to know what that angle is. Well, unfortunately though, because we could have vectors in 4 space, 5 space, 6 space, we can't draw it to explain why it works. Oh sure, we could draw it in, say, a plane or in 3 space, but even then, once it gets to 3 space, it's a little hard to see why. So there's an important theorem called the Cauchy-Schwarz inequality, which states that if you have two vectors in Rn, then the absolute value of their dot product is always less than the product of the magnitude of those vectors. And you can only have equality if the vectors are equal. Or at the very least, they're multiples of each other. Now what this inequality implies then is that if you ever take the dot product of two vectors and then divide by the lengths, the product of the lengths of those vectors, that particular quotient is always a number between 1 and -1. And it can equal 1, it can equal -1. This means in that quotient, the dot product of u with v divided by the product of those lengths, u and v, that's a number between -1 and 1. And that means that you can find some angle, so the cosine of that angle is equal to that quotient. This is the definition of the angle between vectors. And it just so happens to be the right angle. If you look at it in terms of, let's say, a plane, the angle between two vectors has to satisfy this particular equation. Let's just use it really quickly. I want to find out what's the angle between these two vectors. So I'm going to call them u, which is 1, 2, 3, and I'll call it vector v, which will be 2, 2, 1. To use the formula, I need to know what is their dot product. So that dot product is 2 times 1, or 1 times 2, which is 2, plus 2 times 2, which is 4, plus 3 times 1, which is 3. That dot product, therefore, is 9. I need to know the length of u, which is the square root of 1 squared, which is 1, plus 2 squared, which is 4, plus 3 squared, which is 9. That's the square root of 14. And I need the length of v, which is the square root of 2 squared, which is 4, plus 2 squared, which is 4, plus 1 squared, which is 1, and that is the square root of 9, which is just 3. So the cosine of this angle that is between the two vectors has got to equal that dot product, which is 9, divided by the product of the lengths of the vectors, which is 3 times the square root of 14. So that would then be 3 over the square root of 14. So theta, this angle, is therefore the inverse cosine of 3 divided by the square root of 14. That's the exact answer. If you want to know approximately what it is, you would just type it into the calculator and then follow whatever rules that are given to you to round the answer to however many decimal places. Usually we go 2 decimal places for angles. We go 3 decimal places for radians. Okay, now that you have that, the next thing is we want to use that to describe a certain kind of special relationship between vectors. See, if their dot product is 0, then the angle between those two vectors must be 90 degrees. The reason is the cosine of that angle is equal to this fraction. But if u dotted with v is 0, then the cosine of the angle, that's just 0. And there's only one angle between 0 and 180 whose cosine is 0. That's 90 degrees. So we will say from now on that two vectors are orthogonal, not perpendicular. They're called orthogonal if their dot product is 0, and vice versa. If their dot product is 0, then they're called orthogonal. Also notice that you can get from this nice little equation that if their dot product is positive, then the cosine of the angle is positive, and therefore the angle must be acute. If the dot product is negative, then that fraction is negative, so the cosine of the angle is negative, which means the angle is obtuse. So we get this nice relationship. All right, proof break time, at least once. Many of the applications that you're going to see will require to have a fundamental understanding of the algebraic properties to get a feeling for why things work in general, because we can't always draw them. In the long term, after about 2/3 of the way through the course, vectors are not things you can see or draw anymore. They're just going to be objects that have relationships between them. So because of that, you need to build up that algebraic muscle in order to get ready for those moments. But I can't spend time proving everything. I just can't. I'm going to leave a few things for you. And you might notice in homework, there's plenty of problems, plenty of proofs, theorems in the book that they say in the theorem, the proof is in your homework. So it's because at this point in college, you're expected to start doing that. You're expected to start not just being hand-fed everything, and instead deriving proofs and theorems on your own. Now, this is your first course that happens. Because of that, and because I'm not really interested in seeing how well you write proofs right now, because I know they're going to be bad, because you need a lot of training. Instead, I give you what we call guided proofs. A guided proof is where you're given all the necessary statements. All you have to do is figure out what order they go in. And in that list of statements, some of them are just false. So you have to know which ones not to use. So then you essentially have all the ingredients to make the pie, the proof. All you got to do is figure out how to put it in the right order. These next two things are two of them. So as another theorem, if I gave you two vectors u and v, then you have the Pythagorean theorem. And this really does make a right triangle in space if the vectors u and v, if their dot product is 0. Because in their dot product, if they're 0, the angle between those vectors is a right angle. So u and v form the legs of the particular right triangle. Just have to put them head to tail. And the vector uv is that diagonal that connects them between the tail of u to the head of v. So in picture form, It makes sense that the length of u plus v squared is equal to the length of u squared plus the length of v squared. But that is true if and only if the dot product between u and v is 0. If it isn't, then you get what's called the triangle inequality, which you learned a long time ago in arithmetic, which says in this case that the length of u plus v is always less than or equal to the length of u plus the length of v. Again, I'm not interested in proving either of these. One of them, the Pythagorean theorem, I actually essentially already have. If you go back and look at this video, I've left little breadcrumbs of the proof. A little bit here on this slide, a little bit here on that slide. All you got to do is put it together. The triangle inequality, though, that one's a little harder to see. That proof is not actually among all the slides I've done, but all the tools you need are among them. Okay, well, now that you have that, you need to have a reason for why to do the things we do. So I've introduced a law of operations, I've introduced a law of properties, but I haven't really done anything yet in order to apply this to anything really fun, because we're just building up a list of tools for later on. Properties and definitions, though, lead to applications many times. In fact, many times applications are what drive these definitions. But also, these applications and properties can lead to new concepts by just generalizing what you've done to a more broader case. So then what I'm about to do is to show you how to make a shadow of a vector upon another vector. That's called projection. The idea of projecting vectors upon things is one of the fundamental problems in algebra, at least in linear algebra. There's quite a number of applications that actually boil down to projecting a vector upon a space of vectors and interpreting what that means. So I'll show you how to find that projection, and then we'll just do a quick problem. Really easy. So the process of finding a shadow of a vector upon another is called projecting the vector upon the other. So given two vectors u and v, same number of components, so they're both from Rn, whatever n is, to find the projection of the vector u upon v, denoted as this notation, projection subscript v onto u, think of the projection sub v, think of that like an operator. It's like the name of a function. So then this part here, that's the name of the function, and of u, that's the input. Think of it as a vector with just two properties. This projection is going to be parallel to u. Being parallel to a vector means that they're multiples of each other. They're in the same direction. Or at least they're in the opposite directions. And then u minus the projection has got to be orthogonal to v. I've drawn a picture for you. So I drew in the vector u and the vector v, and I projected u upon v, like making a shadow of u upon v, as if the sun is beating down upon u, directly down upon v, to make the red vector the projection of u upon v. Notice that that projection, since it's going straight down upon v, u minus the projection has got to be orthogonal to the projection. So then the red vector and the blue vector, when you add them, you get the vector u, and the projection and u minus the projection are orthogonal to each other. So the question then is great, but how do we actually find this projection? What's the formula of it? To do so, we just use the properties we already have. So let's say I'm going to call the projection of u upon v, I'll just call it the vector p to make it shorter for now. But p is going to be parallel to v. That means if it's parallel, that means it must be a multiple of v. So p is some scalar times v. All we have to do then is to find out what the scalar is. Because we just find the scalar, we multiply it to v, that's the projection. But we also know that u minus the projection, u minus p, dotted with v has got to be 0, because v and u minus the projection is going to be orthogonal to v. Okay, so now all we have to do is take these things together. In the second statement, plug in what p equals, p being k times v. You then get this algebraic statement. Notice that u is known, v is known, k is the only unknown thing. Just use the properties of dot products, distribute the dot product v through, and solve for k. When you do so, you'll get that k is u dotted with v divided by v dotted with v. So the projection of u upon v is this scalar times v. So it's u dotted with v over v dotted with v times the vector v. Easy. That's the projection of u upon v. That's the shadow of u upon v. So let's just do it. I want to find out what that projection is. It's really very simple. In order to find the projection of the vector u upon vector v, that would then be, I need to take u dotted with v all over v dotted with v, and then I just multiply it by the vector v. So that is u dotted with v is 1 times 2 is 2, plus 2 times 2, that's 4. And in the denominator, I have v dotted with v, so it's 2 times 2, which is 4, plus 2 times 2, which is 4, and that's times the vector v, which is 2 comma 2. That would then be, you'd have 6/8 times 2, 2. And if you want to multiply that out, you can, in order to get 12/8 comma 12/8. But I think that you'll notice, that there was a common factor with v. Notice that there was a common factor with v. So because of that common factor of v, you can actually take that scalar out. Whatever you're projecting on, not what you're projecting with, but what you're projecting on, if you want to take the scalar out, all you're doing is changing the length of what you're projecting upon, not the direction of it. So you should find that if you take the scalar 2 out of v and do this process all over again, you have to get the exact same projection. And you do. I welcome you to go sit down and try to do it algebraically. Don't try to do it with just numbers to see why that would be true. But it's a clever little trick that when you're projecting upon a vector, if there's a scalar multiple that you can take in or out of that vector, you can do so and the projection will not change. That then gives you a basic introduction to the dot product, projections, angles, distances, and magnitudes of vectors. These are the major operations we have between vectors. Notice for those of you who have had Calc 3 that one thing I'm leaving out is the cross product, because we completely don't care. The cross product can't really nicely be generalized up into higher dimensions where we actually care at all. So we don't introduce that. That means then for all homework problems, if you've had Calc 3 and you feel compelled to use cross products at some point, don't. Keep what you have and use only what I've shown.